I go into that. Remember, I had some I posed some problems, namely for degree and genus equal to 7 and 4, 8 and 5, and maybe also 8 and 6 with S rational. Find the linear system. So, in fact, we'll get back to that a little bit later, and then we'll also see linkage constructions for these surfaces. So this will be kind of a plan as prime examples towards the second part of the lecture today, to look at these three types, these three kinds of surfaces. So D is the degree and pi is the genus of a hyperplane section. Okay. So now to linkage. Well, actually before I say anything about linkage, I will consider the following situation: that I have my surface S and it's inside some hypersurface F. Hi. So this is my surface and this is my hypersurface inside P4. Okay? Of course, all surfaces in P4 are on hypersurfaces. All surfaces on P4 are on hypersurfaces. But what I want to say something about today is, if I start with a surface and I take a hypersurface that contains it, what can I say about this hypersurface beyond just containing it? Well, that's kind of a strange question, maybe, but let me state the kind of thing I'm after. Is F smooth? When S here is a smooth surface. Of course, if I take, there might be very many singular ones, but one could ask, can you find a smooth one? Well, I'll give you the answer right away. There's a very deep theorem by Bacht and Larsen. It says that if F in P4, or actually I should say F in Pn is a smooth with n bigger than or equal to 4, smooth hypersurface. Then the Picard group of F is equal to the Picard group of Pn. So the Picard group of these two varieties are the same, which means that if F is smooth, then any codimension 2 variety inside F here is actually a hyperplane or a hypersurface section. So let's go back to the surface here. If F is smooth, so let me just put it this way: if F is smooth, then S is equal to F intersected with some other hypersurface G. So this is rather important, you know, in terms of intuition. You don't see this intuitively. You would think if you have a smooth surface and you take a general hypersurface containing it, this hypersurface should also be smooth, but that's not the case. So that's this Barth-Larsen thing. And let me also say just a little bit about why this would be the case. So I'm not going to prove, of course, Barth-Larsen, but I will just give you an intuitive answer in this setting of P4. So assume that S is not a complete intersection. So assume that the surface S inside F is not the intersection of F with another hyperplane. So assume that this is not the case. And say that F is the zero locus of a polynomial F, and that S, say, is a, let me just now say local, it's a smooth surface, so locally it's a complete intersection. It's a local complete intersection. At every point I can find two hypersurfaces that generate the ideal at that point. So let me put it this way here, G and H so locally at the P point. So just we picked some point on S and we found some surfaces here that hypersurfaces that generate the ideal locally there. I mean they cut out the thing. Then I can write F as AG plus BH for A and B functions, polynomials. Because F contains S. So if the ideal here is generated by these two guys, then I should have an expression like that. Okay? And now is the clue, right? Now you see I have here four polynomials, four functions. And in P4 they have a common zero. Four polynomials have a common zero in P4. So Z of A, G, H and B, this is not empty and it is a singular point of F. It's a singular point on F because so the zeros of all these things is certainly a point where on F, and also both of these functions vanish there and both of these vanish there. So I have actually a singular point there. So this is the This is the basic idea. So maybe it's easier to convince you, even if so if I think of the following situation, if P2 is inside F, if you have a plane, really a plane inside F, then the ideal of this here is just say x and y, and the polynomial f is then x times some a times some x plus b times some y. That's the form of this. I'm not saying this one here, but f. Right? And then you see all of these guys are polynomials, honest polynomials in this case, and they certainly have some common zeros. You have 4 hypersurfaces in P4, they have some common zeros in the plane, and those points will be singular on F. Those points will be singular on F. Okay, so that's what this is about. So that's why a surface inside a smooth surface is always a complete intersection. So this, on the other hand, so if I start with any general hypersurface containing S, this will certainly be singular along this thing. In particular, in those cases where the surface is not a complete intersection. I mean, we've seen these as the Veronese surface and the elliptic scroll. They are not arithmetically Macaulay, so they are certainly not complete intersections. So whenever you have a hypersurface containing them, that hypersurface will be singular somewhere. Will be singular. It's kind of counterintuitive, but it's very important, you know, that this kind of thing happen. It has to do with the small codimension, as we see here. Okay, so let's look at so I cannot iterate this, say this often enough, you know, because it actually says a little bit more. If you think about the Barth-Larsen theorem, I said, any surface in a smooth hypersurface is a complete intersection, whether it's smooth or not. You know, any surface is a hyper. But let's use that somehow, or let's look at the case S inside a quadric. So what we know, if Q is smooth, then S is a complete intersection. Is Q intersected with some F for some F. But if Q is singular, then what happens? Let's see whether we can deal with the singular case. And so of course singular quadrics, they do appear, there are such things. Since I want S to be smooth, this here has to be irreducible, and so it's either a cone over a smooth quadric in P3, or it's a cone over a smooth conic in P2, which is singular in that case along a line. Let me just take the case in one point, where it's singular along one point. So just deal with that case. So assume that Q is singular in one point. Then I can blow this point up, or we can resolve this singularity, and you get the P2 bundle over P1 of the following kind. You see, if you take just this piece here, you see the quadric in P3, and here is the cone point. If I think of this as a rank 3, well, yeah, this is my quadric blown up where the singular point is blown up. Okay, so since this is a map, has a map to P1. The singular one does not have a morphism to P1, but when you blow up, you have a map to P1. And then the Picard group of Q tilde is generated by two elements. Well, the hyperplane divisor coming from Q, or from P4, and an F, which is the fiber of this map here. So if I have a point here, then this is mapped, there's a fiber over this one, like that. So therefore, if I have a surface S in Q tilde, then S is some A times H plus some B times F. The class of S, I should say, on Q tilde. So as in a Picard group. Okay. So I want to determine what are the possible A and B here. And if you compare this with this thing here, this part here is, if B is equal to 0, I get the complete intersection. Something which is a multiple of a hyperplane section. So that's a hypersurface section. But now B different from 0 would give you something else.
You mean S is a strict transform or what?
Yeah. Yeah, I think you're right. I should put a S tilde here. S tilde, right. Thank you. Because I have my S inside here, and now I look at S tilde inside there. So notice that the difference between S and S tilde doesn't have to be much, you know, because the difference between Q and Q tilde is just that I replaced the point with a line, just a P1. So either this line is on S tilde, and then I really have blown up a point, or the line is not on S tilde, and then there's no difference between the two. Okay. So let's try to find that line in a way. Well, if I look at the intersections on the surface, no, on the threefold, I get H3 equal to 2. That's the degree of the quadric, right? And I have F squared times anything equal to 0, because that's two fibers. If I take two fibers and intersect them, I get nothing, whatever I intersect with them afterwards. These are fibers over P. So I put the F squared times F, and F squared times H is both equal to 0. Okay? But H squared times F, this is 1, because the fiber here is just a plane inside P4. So these are my intersections, and therefore if I look at H minus F, that's a divisor. That is certainly a divisor. There are hyperplanes containing a plane, so this is a divisor, and I take the square of this and I measure what happens. If I intersect this with F, I get 1. H squared times F is equal to 1. And also H minus F squared times H, this you'll see by the same numbers here, is equal to 0. So this means that H minus F squared is the class of the exceptional line. Okay. So let me try to explain that once more. I mean, so there's many things, but this is geometry. There's a picture in your head somewhere, and you have to build this picture. You paint this picture. So we start with a singular quadric. So maybe I should even try to draw this quadric. It's singular. It's a cone over a quadric in P3. It's singular at one point. That's my Q. Now I resolve this singularity. I don't really blow it up as a point in P4 or here. But you see there is, for each of these planes here, for each of these lines, you get a plane spanned by the line and the vertex point. So you have two families of planes through the vertex in this quadric. And each one of those families are parameterized by P1. So therefore, there is a P2 bundle. P2 bundle, that's this P2 bundle, over P1 that resolves this singularity. And that what happens is that this is replaced in Q tilde with just a line, a P1. And that P1 is the exceptional line that I'm talking about over there. I can see this in this whole thing because the line, it will intersect the planes in one family, all of them in one point. It will intersect the planes in the other family in -1 point because I blew up. So another way of doing this is actually to blow up the threefold in one of the planes. And you blow up a variety in a divisor, nothing happens except at those points where the variety is not a complete intersection, or where it's not a Cartier divisor. So that's exactly what happens up here. So anyway, this was again to go back to the picture. See, I've identified the exceptional line for this map here, this morphism, as H minus F squared. It has degree 1, it intersects all of these guys in one point. And it is collapsed when you go down. H minus f squared, this thing, this curve, intersected with a hyperplane is nothing. So it's collapsed. Okay? So now I can go back to the surface and see what happens if I multiply this surface with h minus f squared. Right? What do I get? Well, this is AH plus BF multiplied by h minus f squared. So here I get A times, well, H times this is nothing. That's what I computed. But B is equal to 1, so I get B. That intersection is just B. And this is now going to tell us something. I have my surface on Q. I blow up this point and I get my S tilde. And what happens here is that either the exceptional line is on S or it's not. If the exceptional line is on S, then the self-intersection of that line must be minus 1. If it's not on S, then this line could intersect S tilde in at most one point. Otherwise, you know, if there are 2 or more points on that line, those points will come together when I blow it down. And then the surface will be singular in that point. So if S is smooth, so S is a smooth surface, then B must be, so S smooth, then B is equal to either minus 1, 0, or 1. And these are the only possibilities. So if I, so this is in a singular quadric, let me put it this way. The conclusion so if I put it this way, S tilde AH plus F AH or AH minus F. Okay? And so I can write this here as A plus 1 times H plus H minus F. Here is just AH, and here I see AH. I'm sorry, this is not. This is of course not correct. This is. So let me see. How do I want to say this? I want to say A plus 1 times H and then minus H minus F. And here I have H and then minus F. So these are the three possibilities. And now what I'm looking for, trying to say here is, in the middle we have the complete intersection case. These two other cases, what kind of cases are they? Well, I've written it this way deliberately, of course, because I want to think of whatever I subtracted here as the class of a divisor. What kind of divisor is this? What kind of surface is this? If it is effective, F is actually a plane. And H minus F, what could that be? Well, I take a hyperplane containing a plane. If a hyperplane section of a quadric in P4 contains a plane, then the other part of that hyperplane section is another plane, because the complete thing is two planes, right? So in both of these cases, these are planes in the quadric. Both of these guys are planes in the quadric. And so we say that S in Q is either a complete intersection or it is linked to a plane. Or is linked to a plane. And so this is by example an introduction to the theme of linkage. So what I'm saying there, in this particular case, is that S together with a plane, the union of S and a plane is a complete intersection. You see, if I move this piece here over to the other side, it says H minus F plus S tilde is equal to this complete intersection. And also here, if I move this F over to the other side, I get that S tilde plus this F is equal to a hypersurface section. So let me therefore define linkage. So this is going to be geometric. And so two surfaces. So this can be done much more generally, but let me just state it for surfaces. So two surfaces in P4 are linked if the union is a complete intersection. So algebraically one has to be more precise, but this is the version that I'm going to use. Although I'm going to use some general formulas for linkage that hold in great generality. So in particular, my surface S here upstairs and one of these planes are linked if I'm in the first case. And surface S is linked to a plane if I'm in this last case here. So how should I think of these things? Well, the first important thing is two exact sequences. And this is the case, so let me say that S1 union S2 is equal to F intersected with G. So these are the surfaces, and these are the hypersurfaces. And for me now, little f is, and little g, these are the degrees of big F and big G. F and G are degrees. Yeah, so maybe I erase it there so it doesn't get too confusing, but F and G are the degrees of these two. Then there are the following exact sequences. S1 of K S1 of the union, and now it's F plus G minus 5, and then on the other side O S2 F plus G minus 5. And similarly, S1 O S1 F plus G minus 5, and the quotient here O S1 intersected with S2 F plus G minus 5. So let me, so I'm not going to prove anything about these things, but I will again try to build a little bit of intuition on this here. So why do these things show up like this? So what does it contain here? Well, if I look at these terms, F plus G minus 5, what is that? Well, if I look at the intersection of F and G, this is a complete intersection surface. Then the canonical divisor on this complete intersection surface, that is exactly by the adjunction formula used twice, equal to F plus G minus 5. So what I have here is exactly the canonical divisor on the complete intersection. And so now if you have this union here, think about this union. This is now equal to this, right? So now if I take the restriction of the canonical divisor to S1 this as a divisor, then this here is equal to when I restrict the canonical on the union to one of the components, I get the canonical on this component plus the intersection divisor plus S1 intersected with S2. So if you think of this for curves, if you think of these two things as just curves, here is the canonical divisor on the curve, on that one component, and here is the intersection with the rest. And this altogether is the restriction of the canonical divisor on on the whole thing to one component. So in fact I would put it up here, analogy for curves. So this means in our case for the hyperplane sections, if you look at the hyperplane sections, then I get 2 pi 1 minus 2. That's the canonical on, let me put it on this side here. Let me try to write it properly. So then I would need to intersect this with a hyperplane again, so therefore I get here f plus g minus 4 now because I am on the hyperplane section times the hyperplane divisor. So this is, if you take the degree, this is going to be just d1, where di is the degree of si. On the other side here, I have first 2 pi 1 minus 2, and here I have some number, some intersection number, right? Similarly, I would get f plus g minus 4 times d2 equal to 2 pi 2 minus 2 plus the same number, right? If I just switch the 2 to the other side. So what I get from this is, in fact, if I subtract the 2 here, the 2 lines, then I get 2 times pi 1 minus pi 2 on this side, and on this other side I get f plus g minus 4 times d1 minus d2. So this is the formula that I can use to see what is the genus of the other side if I start with 1. I have eliminated the numbers here. I could compute those numbers also if I wanted from the same formula. Okay. So now let's actually use this a little bit for surfaces. to get from one to the other. So so let S1 be the Veronese surface. S1 is the Veronese surface in P4. And now I take F and G, general cubics. In the ideal that contain S1. So I didn't say this before, but the ideal of the Veronese surface is actually generated by cubics. So there are plenty of them, and since they are all generated, the other side, you know, when you link here, I'll get a smooth surface for a general choice. So let's see. Assume S1 union S2. So maybe I should have written this the other way around. To start with the intersection of the two. It contains S1, therefore it contains something else also. Whatever that is, I call it S2. These two are cubics. So the complete intersection of those two is a surface of degree 9. Right? The complete intersection of those two is a surface of degree 9. So the degree of S2 is 5. Because this was D1 is equal to 4. Right? I know a bit more. I know that pi1 is equal to 0. The genus of hyperplane section of the Veronese is 0. So now I have computed or down there, and I've computed the pi2. I put in here. So I could write this over here. Maybe some can see it at least. Well, yeah, so now maybe I do it over here just quickly. So 3 plus 3 minus 4 times the difference of the 2 degrees. So D1 was 4 and D2 was 5. So this is minus 1 is equal to 2 times 0 minus pi2. So here I get 6 minus 4 is 2 times minus 1 is minus 2 is equal to minus 2 pi2. So pi2 is equal to 1. So I get 1 here. I get the 1 there. So I have a surface of degree 5 and genus 1. And this we've seen a couple of times. This, I hope, is an elliptic scroll. It's an elliptic scroll. So let me just show you from the sequences that at least it is irregular. So you get something smooth because it's generated by cubics, this the ideal here. But let me show also it's irregular. And then I just use this one sequence here. I start with O S2 now of K S2. And then I get F intersect with G. And now F plus G minus 5. Both of them are 3, so minus 5, that's H. That's just 1 here. And then I get O S1 of 1. Like that. And I look at the cohomology, of course. And I see in the middle here, this is a complete intersection, so I have exactly 5 sections for OH. This is the Veronese surface. This is the Veronese surface. I have 6 sections for OH. It was a projected Veronese surface. So therefore, this thing here is at least 1. I get something irregular. And in fact, one could then go on and show that this is 0 and this is exactly 1. Here is a 0. Here is a 0. So this 1 there, so since this was a projection, I get the irregular surface there. And it is exactly this elliptic scroll. So this is a equational way of getting an elliptic scroll. You start with a Veronese, take 2 cubics, and then you link it, and you get this. So in fact, I should say here, for those that do and should, of course, do compute with Macaulay or anything, you know, the algebra here is that the ideal of S1 is equal to the ideal of the complete intersection divided by the ideal of S2. You just take the quotient. That's how you do this ideal theoretically. So on the computer this is very easy to do. Okay, so that was the elliptic scroll. Now why don't we continue with this here. Let me see, where should I take it? I think I should need, I'd like to use those things. So let's start with the elliptic scroll, S2. And then F, a general cubic. G, a general quartic. General cubic and general quartic containing S2. So this means I said F and G is equal to S2 union some S1. Maybe I should have called this S3 now, but I go back. So I just link. And the reason why I do this in some way, if I start with, I'll just say this more generally, if I start with a surface which is arithmetically co-Macaulay and use linkage, then I will get a new surface that is arithmetically co-Macaulay. And this is something you see from these sequences here, because in the middle here you have no cohomology. This is arithmetically co-Macaulay. So if this one is also arithmetically co-Macaulay, I get all zeros here for cohomology, and therefore you also get all zeros there. So arithmetically co-Macaulay is preserved, you know, with linkage. So therefore, to get new surfaces that are not arithmetically co-Macaulay, not defined by maximal minors of some matrix, I need to start with something which is not arithmetically Coley, so that's why I started with Bernoulli surface here, and now the elliptic scroll is the next case, and I go on. So let's see what I get. So d2 is of course 5, and pi 2 is equal to 1. So therefore d1 in this case, well, this is a quartic and a cubic, so this has, the union has degree 12. Means that d1 is 7. d1 is 7, right? And then pi 1 is equal to whatever I could get out of this formula here. Well, so what do I get if I put in 3 and 4? 3 plus 4 minus 4, that's 3 times the difference of the 2 degrees. 7 minus 5 is 2. Is equal to 2 times pi 1 minus 1. Okay, so this is 6. So therefore 2 times 3 is 6, so pi 1 is 4. Pi 1 is 4. And now I put them into the sequence and see what I get here. S2, yeah, let's see. Yes, let me put S1 there. Of the union, and now it was 3 plus 4 minus 5, that's 2H. Like that. Okay. So now I can do this in different ways, of course, but so first of all, the elliptic scroll is not contained in any quadric. This you could actually prove by the argument we had in the beginning of this hour. We know that the smooth surfaces on the quadric, they are always linked to a plane, or they are complete intersections. Since this has degree 5, it couldn't possibly be a complete intersection on the quadric because it is odd degree. And if it's not, then it's linked to 3 to a plane. But that means that the hyperplane section is of genus 2 and not 1. So that fails completely. So the quadric, now the elliptic scroll is not on any quadric. Therefore this map here is injective. There's no quadric here that vanishes here. So therefore I have nothing. I have nothing here. No K1. Also on the elliptic scroll I can show easily that you have exactly the right number of quadrics. That this is actually quadratically normal. So therefore, since this here is 0, I get a 0 there also. So altogether this means that chi of S1 is equal to 1. Here I have H0 of K, and this is H1 of K. H2 of K is of course the same as H0 of O, which is 1. But these other ones are 0, because these two are isomorphic. So chi is equal to 1, and then you're very close to see a rational surface. Rational surface. And so now it's time actually to look at these cases here. Because 7, 4, that's exactly what I'm looking at here. Degree 7, pi 1 is equal to 4. That's exactly the kind that I'm looking at there. So this is a construction of such a surface. This is actually a construction of such a surface. So now I want to go back to the I would actually like now to go to these three to use the adjunction to find the linear system. And then in the end, we'll go a little bit back and forth between the two. So this is rather powerful. I didn't say precisely what you need, but well, I said it maybe orally, I didn't write it. Namely that if the ideal of the elliptic scroll is generated by cubics, then the general linked surface will be smooth. Right? So this is it's like a Battini argument. If it's not generated by cubics, then you might be in trouble. It's a part of a hyperplane section. It's certainly because the quadric is contained in the hyperplane, and so you have this quadric and this curve here, which is of type AB, say, where A plus B is less than or equal to 8. Well, it couldn't be equal to 8 because then the whole hyperplane section is on the quadric. But it could be slightly less, and what happens here is that this here is actually equal to 7. It's a type 3-5. I'm sorry, 2-5. And the difference is just the exceptional line. So it's one of the curves. So there is an exceptional line in this case. So there is one of the hyperplanes containing that line, where the residual curve, the rest of that hyperplane section, is contained in the quadric. It's a type 2-5 on the quadric. So now what you can look at is what is S union Q inside two quartics. If I take two quartics, I get these two surfaces, two quartics containing S. I get S and Q, and I get something else. Something, if this was S1, I get something S2 over here. What is this S2? This has degree 8. This has degree 2. The complete intersection has degree 16. So this has degree 6. And with this information here, I have to shortcut, I'm sorry, a little bit, but with this information here, you can actually compute, because here you have the intersection between the two, these two. The intersection between those two is this curve of degree 2-5, or type 2-5 on the quadric. So I can find the sectional genus of this one. And so in fact, I get that pi 2 is equal to 3 by the formula over there again. And in fact, that S2 is rational as type 6-3 surface, you know, that what we had before. Exactly this surface that the surface which is given by quartics through 10 points. I could now have left it at that, but I cannot do that because so let me just say that once more here. I take my original surface and this quadric of 5 secant lines, the union of those two, and look at two quartics that contain them. Then I get some linked surface. And I can use the formulas that I've had over here to compute all the invariants of S2, since I know the intersection of those two. I know everything. I don't need the linkage to compute everything here. And so from that I can get the invariance of this one. And that is what I'm saying, that's this rational surface of thing here. So the question is, if I know this, could I get the equations of S1? Could I get the equation from S1? I know because I know how to get this guy. That's just a 3x4 matrix of linear entries. That's an arithmetically Common-Macaulay surface. That's a quadratic surface. Should be easy to get that guy. So if I just put those two together, then link it back the other way to get S1. So what I'm jumping here is a little trick, how do I put them together? How do I put those two together? Because this here means that Q intersected with S2 is actually of type 3, 0 on Q. You see, 2, 5 and 3, 0, those two curves together is the intersection of Q with all the rest. And by the formulas over there, they should be exactly 5, 5, 5. So that's the 3, 0 curve. And 3, 0 is just 3 skew lines. 3 skew lines. I want the intersection of this surface with this guy here to be 3 skew lines. So S2, that's 4, 1 to the 10. And then Q is whatever it is. But Q intersected with S2 should be 3 skew lines. So again, now we're into geometry again. Is this possible? These skew lines should be on the surface, and the only lines on the surface are these 10 lines that we see here. You see 10 lines, one for each of these. These are the exceptional lines on the surface. So if I take any two of those, they will be contained in a hyperplane. That's fine. But any three, can I find 3 of those in a hyperplane? No, not for free. There's no way I could get this for free, because if you have 3 in a hyperplane, it means that there is a quartic with 3 double points and 7 simple points, and that's not going to work. So I cannot take any Bodega surface. This is called a Bodega surface. I cannot take any such surface. I have to start with, I could start with these 10 points with 3 of them are nodes of a quartic and the rest are simple points. I just start with a particular one where 3 of these lines are inside the hyperplane. And I can construct those from the linear system. And then I can get the Q. And then I can get this surface over here. And that's actually, together with this other thing with the positions in the plane, this is actually where the fun starts, in this business, where you have to be, it's a bit more tricky, you can build these with linkage or with linear systems, these kind of things. Okay, I think I should stop there. I'm certainly over time. Okay.